Welcome to mathematical physics. Have you ever wondered how we can predict the exact position of a moving car? Or visualize the invisible sound waves traveling through the air? Today, we are going to learn about plotting elementary functions. This is the very first step in reading the visual language of the physical world. By the end of this video, you will understand how to turn mathematical equations into clear visual stories that reveal the hidden behaviors of the universe. To begin our journey, let us talk about plotting polynomial functions. Why do we care so much about plotting these basic shapes? In physics, almost every simple motion or force can be modeled using linear or quadratic functions. Imagine tracking a car driving down a straight highway. If you mark its position every second, you are plotting a mathematical function. The horizontal axis, usually called the x-axis, is our independent variable, like time. The vertical axis, the y-axis, is the dependent variable, like position. By looking at these shapes, we can instantly understand the relationship between two variables without ever needing to read a confusing table of numbers. Now that we understand what a plot is, let us look at the simplest polynomial, the linear function. This formula comes from the idea of a constant rate of change, like moving at a steady speed. The equation is y equals m times x plus c. Here, y is our output and x is our input. The symbol m represents the slope. It tells us exactly how steep the line is. If m increases, the line becomes steeper, meaning y changes faster. The symbol c is the y-intercept, which is where the line crosses the vertical axis when x is 0. If c increases, the entire line shifts upwards without changing its tilt. Before we move on, let us see this with a concrete example. A physics student is walking down a hallway. Their position in meters after x seconds is given by y equals 2x plus 3. We want to find their exact position at 4 seconds. To plot a straight line, we only need 2 points. First, we plug in x equals 0 to find the starting position, which gives us 3 meters. This is our y-intercept. Next, we plug in x equals 4. 2 times 4 plus 3 equals 11. So at 4 seconds, the student is at the 11-meter mark. Connecting the points 0, 3 and 4, 11 with a straight line visually proves the student is moving forward at a constant rate of 2 meters per second. Having mastered straight lines, we now step up to changing rates of change, modeled by the quadratic function. This formula, y equals a times x squared plus b times x plus c, creates a U-shaped curve called a parabola. The highest power here is 2, which is what causes the curve. The coefficient a is crucial. If it is positive, the parabola opens upwards, like a smile. If it is negative, it opens downwards, like a frown. As the magnitude of a increases, the parabola becomes much narrower, indicating a faster rate of growth or decay. The coefficient b shifts the curve left or right, while c remains our starting point on the vertical axis. Let us apply this quadratic formula to a real physical scenario. Imagine a heavy ball dropped from a building. Its height, y, in meters after x seconds is y equals negative 5x squared plus 20. We want to plot its path. Because the x squared term is negative, the parabola opens downwards. At time 0, we plug in x equals 0 and get 20 meters. This is the release point. After 1 second, plugging in x equals 1 gives us 15 meters. The ball is speeding up.
After 2 seconds, plugging in x equals 2 gives us 0. The ball has hit the ground. Plotting these points reveals a smooth downward curve, perfectly visualizing the accelerating drop due to gravity.
Now that we have calculated the points, let us look at the actual graphs. On this diagram, the horizontal axis represents time in seconds, and the vertical axis represents position or height in meters. Notice the blue line. It starts at 3 and rises steadily to 11. This straight line represents our constant velocity example. Now look at the red curve. It starts high at 20 and bends downwards, getting steeper until it hits 0 at 2 seconds. This parabola represents our falling object. Linear functions show us constant rates using straight lines, while quadratic functions reveal changing rates, like acceleration, through curves. We have seen how polynomials describe simple motion, but what about more complex events? Have you ever watched a pendulum swing or heard about radioactive decay? These cannot be described by straight lines or parabolas. Instead, nature uses transcendental functions, which transcend simple algebra. Exponential functions have the variable in the exponent, creating graphs that shoot up infinitely fast or flatten out toward 0. Trigonometric functions relate angles to ratios, producing graphs that wave up and down in perfectly repeating cycles. These plots are absolutely mandatory for advanced physics. Without them, we could not understand sound waves, alternating currents, or radioactive decay. This brings us to the mathematical formula for exponential decay. The equation is y equals a times e raised to the power of negative lambda x. Let us break this down. The symbol a represents the initial amount when time x is 0. The letter e is Euler's number, a fundamental constant roughly equal to 2.718. The symbol lambda is the decay constant. It dictates how fast the quantity shrinks. If lambda increases, the curve drops to 0 much faster, meaning the decay is more aggressive. If a increases, the starting point is higher, but the overall swooping shape remains exactly the same. Let us see how this formula works in a laboratory setting. A scientist is studying radioactive material, starting with 100 unstable atoms. The remaining atoms after x days is given by y equals 100 times e to the negative 0.5x. We want to find how many atoms remain after 2 days. At day 0, we plug in x equals 0. Anything to the power of 0 is 1, so we start with exactly 100 atoms. This is our y-intercept. After 2 days, we plug in x equals 2. The exponent becomes negative 1. The value of e to the negative 1 is roughly 0.368. Multiplying by 100 gives us approximately 36.8 atoms remaining. The curve swoops down rapidly, then gradually slows. Now that we have modeled decay, let us look at things that oscillate. This is the standard equation for a sinusoidal wave. Y equals a times sine of k times x. The symbol a is the amplitude. It tells us the maximum height the wave reaches above the center line. The sine function itself creates the repeating up and down pattern. The symbol k is the angular frequency, which determines how tightly packed the waves are horizontally. If a increases, the wave gets taller and deeper, representing a louder sound or brighter light. If k increases, the waves get squished closer together, meaning the cycles repeat much faster. Let us apply this to a tuning fork producing a sound wave. The air pressure variation is y equals 5 times sine of pi times x. We want to plot one full cycle. First, we identify the amplitude, which is 5. Next, we find the period by dividing a full circle, 2 pi, by the coefficient pi. This gives us exactly 2 seconds for one full cycle. At 1/4 of the period, which is 0.5 seconds, the sine function reaches its maximum. 5 times sine of pi over 2 gives us a peak pressure of 5. The wave starts at 0, peaks at 0.5, crosses 0 at 1, hits a minimum, and finishes the cycle at 2 seconds. Let us visualize these two powerful transcendental functions. On the left, we have the exponential decay graph. Notice how the blue curve starts high at 100 and drops dramatically, passing through 36.8 at day 2, before slowly flattening out towards 0. It never quite touches the axis. On the right, we see the sinusoidal wave. The red curve starts at 0, rises to a peak of 5, drops down to -5, and returns to 0, completing one beautiful symmetrical cycle in exactly 2 seconds. These plots allow us to literally see the fading glow of radiation and the heartbeat of a sound wave. We have covered a lot of ground today, so let us summarize our key takeaways. First, plotting is not just drawing lines, it is translating mathematical equations into visual stories that describe the physical world. We saw how linear and quadratic functions perfectly model constant velocities and accelerating objects. Then, we explored transcendental functions, where exponential plots revealed the dramatic swoops of radioactive decay, and trigonometric plots captured the endless, repeating rhythms of sound waves. By mastering these elemental plots, you now have the foundational tools to visualize the invisible forces, sounds, and energies that surround us every day. Great job, and keep practicing.